Welcome back. This is P1 Part A tutorial, where we're going to talk about fixed-size memory pool management. As usual, this is the lab manual reading list. Chapter 2 and Chapter 3 are the main parts. These are the corresponding sections. So this talks about the overall API, you need to study it. And then Section 2.2 gives the detailed specification about memory management API. Then starting from Chapter 3, we're going to talk about processes, and the very first one is the not process. So you want to take a look at this one. And then the 3.3.1, we talk about 6 user-level test processes where we specify the output format. I've updated the lab manual with the updated output format requirement. Please pull the latest lab manual from the GitHub. And Chapter 4 talks about the RTS initialization. During initialization, we set up data structures. So this one basically means for any kernel objects you're going to create, you need to do initialization, the data structure initialization. And for Chapter 6, it's FAQ, so you can skim through them to find out the relevant questions. And the recommended reference for doing this lab is the OS, the Operating System's 3 Easy Pieces, Chapter 17. This is a good reference on dynamic memory management. Actually, it talks more than what we need. I would like you to pay special attention on section embedding a free list. This is not a required reading, but by reading it, you will find doing this lab a lot easier. The basic requirement of Part 1 of the project, or P1, is to provide a multi-programming environment like kernel that supports simple memory management and a fixed priority preemptive scheduling. The first 2 points are Part A. Well, this part is almost done for you by the starter code, and you'll be focusing on the simple memory management. And in Part B, you're going to expand this multi-programming environment to support a fixed priority preemptive scheduling algorithm. Here are some assumptions that are very specific to embedded systems, and that is for our lab project. Our lab project is mainly targeting the embedded system. So all processes are known. What does that mean? It means they are created at startup time, so we know which processes will be created, and we don't create any new processes during runtime. Second of all these processes, they know each other, so they know each other's PID. The second assumption is that processes are not malicious. You may wonder why. Well, typically on the embedded systems, we have different processes. They collaborate together to achieve some common goal. So that's why we make this assumption that they are collaborating. They don't really purposely harm each other, let's say try to damage the other process stack or things like that. We have common.h file that lists all the PIDs and all the priorities and the memory size and the number of memory blocks and some commonly used macros. So from a software developer's point of view, the P1 requirement is to write a couple of functions, or what we call user API, or more specifically, they are system calls. The first set of system calls is memory management related, and so we have a system call to get a memory, and we have a system call to release a piece of memory. And you can see this is very similar like malloc and free, with the exception that we don't really specify the size of the memory, because every time we request, it's always a fixed size, the same size. This simplifies people's life. So this is the Part A of the P1. And then Part B will be focusing on the processes management, and we have 3 APIs, and I'm going to talk about it when we start the tutorial of Part B. RTOS primitives or system calls must be executed indivisibly. So we define a private kernel function, atomic on or off. So this is only for concept. The actual implementation varies. On means I enable the atomicity. So the first executable statement in each primitive needs to have this atomic on. Okay, and then once we finish doing our kernel function, then before we return to the user space, then we do atomic off to basically disable the atomicity. So that's basically the concept of atomicity on and atomicity off. So how do we program it? Well, usually people do this code in assembly. Remember, all system calls, they are SVC handler. So the first thing we enter the SVC handler, we can turn off the interrupt. So we have atomicity on. Now once we're done returning from SVC handler to the user space, then we can turn the interrupt back on, and then that's atomicity off. Another part of the P1 requirement is to write processes. You're going to create 7 processes. One is a null process, the other 6 are test processes. The null process is a system process which has a reserved PID of 0. It does nothing in the infinite loop. The reason why we need it is because the operating system needs at least one process that is always ready to run so that it can execute the CPU instructions. The operating system always needs something to execute the CPU instruction, and that's the purpose of the null process. And then for the test processes, they have PIDs reserved like from 1 to 6. They're user level processes, and they only call the user APIs. And then finally, you need to do the initialization. You need to initialize your memory, process, data structures during the OS initialization phase. I want to remind you that there are no new processes get created on the fly. All processes are created during startup time. And second of all processes, they never terminate. You will notice when we want to write a process, it is a function, and inside this function, there's an infinite loop. So processes, they never die. So you may notice that I don't really say which part is part A, which part is part B, simply because the memory allocator we're writing is kind of coupled with the process management. So how do we decouple this memory allocator from the process management? Well, the memory allocator we're writing is a blocking version of memory allocator. If this blocking part makes it coupled with the process management. So if we start with a non-blocking version of memory allocator, then we can just be focusing on the memory allocation. In the starter code, I provide you 2 test processes. And if you just do the non-blocking version of memory allocator, you can just use the 2 test processes to test the non-blocking version of memory allocator. Once the non-blocking version works, then you can move on to part B, start to do your process management, and then you can add the blocking feature to the memory allocator. So we will be focusing on the memory pool management in part A. So what does memory pool do? What does memory management do? Well, the memory pool is a simple memory management mechanism. It is a logical division of the main memory. The main activity is to keep track of which piece of memory is free and which piece of memory is not free. So when we divide the big piece of memory into smaller chunks or blocks, and then we need to keep track of who is free, who has been allocated to a request. So that's the main activity the manager does. And the design constraints are we need to use the memory that it manages for the memory management metadata. What does that mean? I need some sort of data structure to keep track of who is free and who is in use. And then I need memory to store this data structure. Where do I put this data structure? And for every dynamic memory manager, they always use the memory they're managing to store this data structure. So there's a still piece gets stolen from the memory that it's managing, and then your data structure gets put there, and then the rest of the stuff you can give it to the user. So that's kind of the trick like nearly every memory manager does. The other thing is you need to design your data structure in such a way so that it can handle arbitrary request sequence. So who calls this memory allocator? processes, right? Who write the processes? User. Operating system doesn't know those processes, what they are doing, when they are going to call the memory allocator. So you need to keep in mind, okay, this will be arbitrary sequence of requesting, coming in, requesting the memory, and also releasing the memory. And the other thing is we want immediate response to the request. It doesn't mean you immediately have to give the memory to the requester. You have to immediately respond to this request to basically let the requester know whether you have memory or you don't have memory. And lastly, very important, once you allocate this memory to the requester, the memory manager cannot arbitrarily modify the allocated block, right? So that's very important. Recall the memory map of our microcontroller. We have two pieces of static RAMs. We will be focusing on managing this piece. This one is entirely free. We don't require you to manage it, but if you want to manage it, you're more than welcome to do so. This will further expand the capacity of your OS. We just talked about that we're going to manage the IRAM1. 32 kilobytes of memory. However, part of this memory is used by the application image, and for our case, it will be the operating system kernel's image. Recall we set up the target memory area, and here we specify the read-write memory area and read-only memory area. This is the target setting for a simulator target. Now we tell the linker to use that memory layout to generate our RTX image. Then under the hood, our specified memory layout turned into a scatter file. Then we got our AXF file. Now we got this image, and we're going to load this image onto our microcontroller. And this will affect the RAM usage, because part of the image will go onto the RAM. So which part of the image goes to the RAM and which part doesn't? Well, this requires us to understand the layout of a simple image. Well, the simple image contains the read-only section and a read-write section. The read-only section contains code, instructions, RO data, basically constant global variables. Read-write section, RW data, which are global variables initialized with non-zero values, and ZI data, which are global variables initialized with 0 values. And you can see the size of each component by looking at the build output from the IDE. And here are just some terminologies. So when we say ROM size, basically this ROM size is the image size. It is the size of code, RO data, and W data, not ZI data, because ZI data is 0. We don't need to know. We don't need to save the ZI data into our file. So when we want to save the .axf file as a file on some media, we only need to save this 3 part, and we call it RO size. And then this 2 part is called RW size, and this 2 part is called RO size. Now I'm going to use the simulator target as an example to illustrate which part of image goes to which part of the memory. When we load the image to the microcontroller, the AXF file gets copied to the ROM. So this is the ROM. This is what we call load view. Basically, we load the code to the microcontroller. But when we want to run the code or when we want to execute the code, we have an execution view of the memory layout. So when we run the code, then the RW data gets copied to the main memory or the RAM. And on top of the RW data section, the ZI data section gets constructed. And so we got this RW section inside the main memory. And you can see the RO part, they stay in ROM. So the free space is between the end of ZI data and the end of the physical memory. I want to remind you, we are managing physical memory. We're not managing virtual memory. So these are the physical memory addresses. So the question is, how do I know the end of ZI data? Well, there's a special symbol defined by the linker called image $blah, this long name. This one, the linker put it at the end of the image. So if we get the address of this symbol, then we know the starting address of the free space. And then this ending address is basically this one, -1. Yeah, so to summarize, we have RTX image using the lower part of this memory in IRAM1, and then this is the free space we need to manage, and we know the starting address of the free space, and we know the end address of the free space as well. So this part basically is what you're going to manage. Now let's take a look at the RAM target memory layout. What happens when we load the RAM target to the board? Well, recall that we have split the RAM portion so that the RO area use part of the IRAM1 and the RW area use part of the IRAM1. And we split them equally. So for the RAM target, the main memory layout is a little bit different, but it doesn't matter from a programmer's point of view because the free space is still between the end of ZI data and the very end address of the physical memory. Well, what happens is we basically use the first half of the RAM as the ROM area, so the RTX image, instead of get it copied to the ROM, it gets copied to the main memory. So now you know why we call it in-memory execution, because the image itself is not on ROM but on RAM. As I mentioned, we do have a second region of memory which is entirely free, and that's the starting address, and that's the size. It's 32 kilobytes. We do not require you to manage it. The more you manage, the more work you need to do. But if you're interested in expanding your RTOS capacity memory management functionality, this is another piece of memory you can manage. Again, this is not required. So you may wonder how I'm going to write program to use this linker defined symbol. Actually, you just extern it. So although it has this $$ thing there, it's just a variable name. So you extern it saying this is externally defined by who? By the linker. And then you get the address of it. And if you want to know the starting address of your free memory, that's the starting address of your free memory. I would like you to start with k_memory.c file, where we laid out the memory map. Actually, we already used a part of the memory. So this is your RTOS image, let's say, and then that's the end of the image. And this dynamic memory pool, this entire blue thing, we actually used a part of it. The top part we used stacks for 2 processes, and the bottom part we use for PCBs and some kernel data structures for the starter code. So what you're left actually is this middle part. You're going to use this middle part to create 32 memory blocks, and each memory block is 128 bytes long. So there will be some left unmanaged free space, and that's fine. So how we are going to do this one? We're going to keep track of who is free and who is not free. Well, the usual data structure is a linked list. But as I said, this is a special linked list because we don't have a function to create memory for the node of the linked list. So you have to embed the pointers to the linked list inside the memory you're managing. So that's what we call using the memory you're managing for the metadata. So all these pointers, they need to reside inside the memory you're managing. So for example, this is an example. I have 3 memory blocks to start with, and they link together. And at a certain point in time, people may request and release in different orders. I may end up like, you know, this one links this one, and this one links back to here. One commonly seen implementation is linked list, and we use linked list to implement a queue. And so we queue up all these free memory blocks, and for request a memory block, we just dequeue a node, and for release memory block, we just enqueue a node. It is a good idea to create a generic purpose queue utility so that this queue can be used to manage other resources. For example, the PCB, the process control block, which you're going to manage in part B of the project 1. There are other implementations as well, but this is a commonly seen one. So the other implementation includes the bitmap. That's one way of implementation as well. And then for the generic purpose utility, the Q utility, you can use C language casting to cast the data structure, the generic Q data structure, to the specific node structure you're managing. Here is a generic memory block data structure. So I have the linked list next pointer. This is the first field in the structure. So if I have a generic purpose queue implemented by using linked list, and that linked list, the first field is also next, then I can do casting to use the generic purpose queue facility I created by using the linked list. Well, you may also notice that I have no memory region variables inside this data structure. So other kernel pointers, usually they are more specific to the memory block data structure we're using. Well, simply because the size of the memory block is determined, right? It's determined at compile time. It is defined in the comment.h file. And then during the OS initialization time, we will create the list of free blocks. And that's a very important step for the OS initialization. Now let's start with the non-blocking memory allocator. So what does non-blocking mean? It basically means the function can return. So if I request a memory block and there's no memory block, the process which makes this request doesn't get blocked. Instead, it will get a null pointer. So here is the kernel version of this function. I put this atomic on and off just to remind everyone this is a non-divisible operation. But in practice, we do this atomic on and off in the SVC handler by disabling and re-enabling interrupts. Okay, so the idea is very simple. We search for our free memory block in the pool. So search our linked list. Is there any node on the linked list? If there is no memory block available, there's nothing on the list, then we return null. Okay, and if there's something, then we basically update the data structure. We basically dequeue a node from the list, and then we return the pointer to the memory to the user. And then that's it. That's our pseudocode. Well, you need this function, this kernel function for P2 anyway, so it's good to start do it right now. And this non-blocking version will also make us decouple from the part B of the process management. And in the rtx_ext.h file, I have also defined the user level system call that corresponds to this kernel function, so that you can call that function. That function is called request_memory_block_nb. You can call that function directly from a process in the test processes we provide to you to test the non-blocking version of the memory allocator. Now let's move on to the blocking version of the memory allocator, which is the required API you're going to implement in P1. So you can consider this K request memory block non-blocking version as something like part of the functionality of the blocking version of the memory allocator. Well, to write the blocking version, first we need to call the non-blocking version. And if we have find the memory allocator, we just return. So exactly same behavior as the non-blocking version. But if we don't find any memory, then we have to do something about the process that caused this request memory block. We need to block it, and we can leave this part to part B. Now we need to take a look at how we are going to return the memory to the memory pool. There's an API called release memory block, and the corresponding kernel function is called k_release memory block. So first we need to do some sanity check, right? So what if I return a memory that is outside the IRAM1 region? Then that's definitely not a valid memory. So do some sanity check. And if we pass this step, then what we need to do is we need to check whether there's anybody that is waiting for the memory or not. If we have somebody waiting for the memory, then we do this part, which we're going to do in part B. But if there's nobody waiting for the memory, there's just no process that is blocked on memory, we just directly put the memory block to the free memory queue or list. So very straightforward. So basically it's a linked list enqueue and dequeue thing for part A. For the OS initialization part, we need to do board system initialization. System init does that, and we need to initialize our UART to do the polling, and then we need to do the memory initialization. So that's basically what we need to do for the initialization for part A. Writing a memory allocator involves a lot of pointer arithmetics, and I'm going to share with you some tips. So first of all, the operation of pointer arithmetic is in the unit of the size of the object the pointer points to. What do I mean? So let's assume I have an integer type of pointer, p, and I give it the initial value of 0. I can use size of int to get the size of an integer on this board, which is 4. Now I do increment p. I increment p by 1. But that doesn't mean increment the p-value by 1. It means increment the p-value by the size of the objects. And that's 4. So after this operation, I get 4. I don't get 1. That's very important. For the struct object, it is very important that we use size of operator to get its actual size, because compiler may add paddings to this struct. This is an example of a struct that the compiler will add padding to. This is 4 bytes, this is 1 byte, and this is 2 bytes. And the sum of the size of each component is 7. But if you use size of, you will get 8, because compiler will add padding after C so that the data object is naturally aligned. Finally, our memory is later ending. To summarize, in P1A, you're going to study the starter code. Be sure to watch the starter code demo video. And then you're going to create your generic linked list queue so that you can use it to manage your memory as well as future OS objects. And then you're going to create non-blocking version memory allocator and deallocator. Here are the references I used to prepare this set of slides. Thank you for your time.